Yes, welcome back, everyone. I think it's time to start the afternoon session on this first day of the conference, and the first speaker will be Basile Grammaticos, who will tell us about singularities and integrability of discrete systems. Let people pass by, and then we can start.
Okay. So, given the question of people, I will make clear that this is not the campus of Paris-Saclay in Orsay. Although the campus is nice, I should have put a photo of our campus. Anyhow, when I first heard about singularities, I wondered, well, what's the interest in them? And then I spent the major part of my career making a living out of the study of singularities. So, but the question remains, why the singularities are interesting? And the best answer is the one given by our mentor. I mean, our means Alfred Ramanujan and myself, Martin Kraskal, who said, well, singularities, that's where something interesting happened. And in fact, this is true. Now, the story starts already in the 19th century, when people started studying integrable systems and where they encountered singularities for the first time. And for me, the turning point is the challenge of Picard, who asked the question, is it possible to define new functions from the solution of nonlinear differential equations, the way we have defined the hypergeometric function through the solution of some linear non-autonomous equation? And of course, the answer is yes. Okay, solve your equation locally on the complex plane, they do analytic continuation, and then the trouble arises because there are branch points. Branch points meaning where your function is exchanging some definition things, for instance, square root with a plus and minus sign. Now, in the case of linear equations, there are ways to address this difficulty. But in the nonlinear case, we cannot because we don't know where the branch points are. The branch points depend on the initial conditions you put in your equations. And so you don't know how to apply all those uniformization procedure. And that's where Penlevé enters, with a bold assumption that there may be equations that do not have movable branch points. That was a bet. And he set out to find them, and he found them. And he found, in fact, we say now canonically, 6 equations which are free of movable branch points, which define new functions, and they are known today as the Penlevé equations, defined in the Penlevé transcendence. Here I give an example of the simplest one you can write. That's the Penlevé 1 equation, and its only singularity is a double pole, no branch points. So the question is anything like that happen in discrete systems? And of course, the answer is yes. Let's start with a simple mapping. This mapping you have over here is an integrable one in the sense that you can write the solution explicitly in terms of elliptic functions. So it's an integrable mapping solvable, in fact, and you see that there are some x at the denominator. So depending on the initial conditions, you may hit accidentally a 0. Okay, hitting a 0, there's not a disaster, because then you iterate your mapping, then the next value you get an infinity, then another 0 appears when you put the infinity in the right place, but then trouble appears, because at the next iteration, you get an indeterminate form. You cannot go beyond this place with your mapping. So what can you do to address this difficulty? Okay, so we invoke a continuity with respect to initial conditions, put some small parameter here, epsilon, then iterate this initial condition, then you find that the next one is 1 over epsilon square. Keep this square in mind, and then again, the next one is epsilon, and then where the indeterminate form was appearing, you go to the limit. Do the limit and find that the next value is not only not singular, not only indeterminate, it takes a finite value and indeed it gives you back the initial condition, the one you started with, and which we have lost during those iterations here. And this property that we discovered, we called it the singularity confinement, meaning that the singularity disappears, the indeterminate form gets determined, and the degrees of freedom are recovered. That's the singularity confinement as we define it here. And since I'm going to talk about more in detail what happens in the mappings, let's see if I iterate some initial condition and what is happening and how the singularity confinement appears in fact. So start with some initial value x0 and then, and then take for x, and take for x1 the value, the value z and iterate. So you can see the sequence, you have a z here, 1 over z squared here, a z here, and after that, you can see that the z appears, but if you put it to 0, you get a 0 over 0 here, and just factors out and it disappears. So this is what singularity confinement is doing, in fact, in the mapping, is introducing some cancellations at that point. And of course, you could have started at any iteration with the root of any of those polynomials and follow the pattern, and you see that exactly you have the same pattern always 0, infinity square 0. And you get, when you iterate polynomials higher and higher order, the degree goes up and up. So it's interesting to start to study the degree and see what is happening indeed in this case. So just look at those polynomials and study the degree of the numerator and denominator as they are. And then you find, when you do that, that the degrees growth like 1, 2, 5, roughly doubling at every iteration. But there are simplifications. We saw that there are simplifications. And when you carry out those simplifications, you find that the growth is just quadratic. In fact, if you look at 1 out of 2, it goes like n squared over 2. So it's indeed a quadratic growth. So this is what singularity confinement is doing to you. It introduces simplifications which lower the degree of the growth of the mapping from exponential here with a ratio of 2 to something that is just quadratic growth. And of course, all those things can be formalized by the introduction of what is called the dynamical degree, which is defined like the nth root of the degree, the limit of the nth root of the degree at iteration n. But you can compute it practically, you can put the equivalent through the limit of this ratio here. And when the mapping is integrable, you are getting a polynomial growth, and this limit here is just 1. The dynamical degree of the integral mapping is this one. And this is something that can be made even more precise, at least for second order mappings, thanks to the results of Diller and Faber. They studied second order birational mappings, and they made precise statements. They proved that when the mapping is integrable, only 3 things can happen. First, the degree growth can be bounded. It grows a little bit, then it stops growing. In that case, your mapping either is periodic or it can be transformed to a projective mapping. Then the second possibility is that your degree grows linearly with n. And in that case, the mapping is linearizable. Linear growth is an indication of linearizability. And the third result is that your mapping can grow polynomially with n, only quadratically. And this is, in fact, this is a major result. We're going to come back to that. Masse-san has shown something much stronger than that. And in fact, when this thing happens, the quadratic growth, the mapping always enjoys the singularity confinement property. So that's a very interesting result. And it's interesting in the light of the next sentence I'm going to say. Non-integral mappings have an exponential growth. But the point is, for the non-integral mappings, they may have singularity confinement property or not. So this is a small problem. Before addressing this problem, I would like you to show exactly what is happening in the non-integral mapping with confined singularities. Let's take this mapping. You know, the only difference from the previous one was the denominator here is the power of fourth. And do the same thing. Put initial conditions as before, then follow z. It's going z here, and then 1 over z to the fourth, then z here, and after that, the z factorizes out, which means the singularity is confined, and the pattern is 0, infinity power fourth, 0. So this mapping has a confined singularity. But when you look at the degrees, the ones you count the degrees that I have here, you find that they grow exponentially with a power 4. Okay, this is something that is compatible with the non-integral character of the mapping. But when you look closely, because of those cancellations here, and count the degree precisely, you find that the degrees grows a little bit more slowly than before. They grow with the ratio which around 3.7. In fact, the exact value is known, it's like that. So singularity confinement does curb the growth, but not enough to make what was exponential growth down to a polynomial one. So at this point, normally, you would ask, what is the interest of a singularity confinement? If I cannot distinguish between an integral mapping, a non-integral one, based on the singularity confinement, so the property is perhaps useless. Well, not so fast. Let me show you a case that is slightly different from the one that we studied before. And this is where we start talking about de-autonomization. Now, this is a notion that we introduced when we tried to derive discrete analogs of the Penlevé equations. Now, the continuous Penlevé equations are somehow non-autonomous extensions of the elliptic functions, meaning that when you take a Penlevé equation, make it autonomous by putting the explicit depends on the independent variable to a constant, then you find an elliptic equation that's satisfied by an elliptic function. So play the same game in the discrete case, start with a mapping that is solvable by some elliptic function, and then assume that the parameters that enter are functions of the independent variable, and try to determine them so as to keep the singularity pattern the same as before. So when you do this, take this mapping and iterate it, ask that the mapping enters some indeterminate form after 3 iterations, and then require that this singularity disappear. You find that this quantity here, an, must satisfy this linear equation here. The solution is just this, and this is a well-known discrete Penlevé equation, among the very first we have found. So by de-autonomization, you take a mapping that where this was a constant and make it a variable, and you get some condition that tells you what is the integral form of this non-autonomous mapping. Good. But now we're going to play a slightly different game. Instead of confining after 3 steps, we say, okay, forget it, we don't confine. We go on. And then after 7 steps, there is again a possibility to confine. And so we say, okay, let's confine at this stage there. This is what it was known by the name of late confinement, but there's just a name, that's not very important. So again, you get a linear equation for an, but when you satisfy this linear equation, you find that the mapping is not integrable. You can compute the degree growth is here, and you find the ratio of dn plus 1 over dn, that is roughly 1.7. So I have confinement here, and I get a non-integral mapping. So you would start thinking, but that I am in deeper trouble than before. Well, that's not true. Now look at this linear equation here, and write its characteristic polynomial. This is the characteristic polynomial over there. You can factorize it and then get this polynomial here, and you can find the Rogers root of this polynomial. And it turns out this one and the value is exactly this. But this is exactly the value of dynamical degree. So at that point, you may start thinking that some miracle happened for this equation. But then when you look at the linear equation here, its characteristic polynomial is just that. And the larger root is 1, which is again the dynamical degree. Of course, it is an integrable equation, so you would expect that. So in two cases, we had the characteristic polynomial given the dynamical degree. Let's try a third one. This was the mapping that we looked at previously. It's a non-integrable one with a confined singularity pattern that's here. And again, I de-autonomize it. And I find this condition for the confinement of singularity. And then the characteristic polynomial is this one. And the larger root is this, which is exactly the dynamical degree. So it's not a miracle. Something is happening. And this is what we decided that was a full de-autonomization criterion, which is the criterion that tells you how singularity confinement can distinguish between a mapping that has confined singularity and it's not integrable from a mapping that has a confined singularity and is integrable. So we have a clear-cut criterion. And perhaps I have to explain what we mean by full, why we don't call it just de-autonomization. Yeah, let me first explain that and then I say something different. Let's look at the HIV mapping, the mapping of Hitarinta and Vialet, which is probably the best known mapping that has confined singularities and is not integral. In fact, it was the first one found like that. So this mapping here has a confined singularity pattern, 0, infinity square, 0, and that's it. It's not integrable. So you can de-autonomize it. Put a free function here, put a free function here, nothing happens. In terms of the equation, the solution are periodic functions, no, not very interesting. But then you make a remark. If I extend my mapping, adding a term here, adding a term here, the singularity pattern does not change. I have the same singularity pattern. And then when I try, this is the mapping that I now de-autonomize. B does not play a role, but when you de-autonomize the mapping by playing with A, then you find the condition here, again, a linear equation for A. That's the characteristic polynomial, and the largest root is this one, which is exactly the dynamical degree of your mapping. So full de-autonomization means that I may, on occasion, extend my mapping by adding terms that do not modify the singularity pattern. I have the freedom to do that. And once I do that, I can consider the non-autonomous forms of this mapping, the de-autonomization, and it turns out that I always get the dynamical degree. And this is not a miracle. This is something that we can prove rigorously. It's something that it was done in collaboration with Alexander Stokes, Massesan, Ralph Willox. So if you have questions on those things, technical one, ask them rather than myself. Good. So full de-autonomization works fine. Clearly, we don't have any case where it does not work. But in some cases, the calculations can be rather heavy. You cannot carry out the calculations. After all, yes, we are limited by what we can do by hand and what the computer can do with computer algebra. So there are cases where you cannot say anything. So what do we do in that case? Well, there are solutions. And the first method I would like to mention is what Rod Halber introduced under the name of Diophantine approximation. And to see how it works, I will get again the mapping that I'm using as an example here in this talk, and start with rational initial conditions and parameters of the equation. So the parameters of the equation and initial condition are rational numbers, and take this thing and iterate it. And you find that. You find fractions that become larger and larger, and when I showed this transparency to Alfred Ramani, he said, oh, that's exponential growth. I said, no, look at this curve, but that's not the exponential curve. If you wish to look at an exponential curve, have a look at this one. This is the non-integrable map. And you play the same game, again with initial conditions that are rational. And now you can see what is really exponential growth. This is the thing. So when you do the Diophantine approximation, just compute the fractions and look at the fractions, how they grow, and you find that the numerator and denominator grow very fast in the case of non-integral mappings and moderately fast in the case of integral ones. And one can do some hand-waving argument and convince yourself that you can get the dynamical degree out of that. So because you can say, okay, the numerator grows roughly like z to the power dn, and then subdominant terms, and then when you take the logarithm to eliminate z, then you find that the ratio of these two logs of two successive numerators or denominators, it will go in the end to the dynamical degree. So this is something that another way to compute the dynamical degree. And in fact, when you look back at those two examples that I have here and do the calculation up to n equal 9 and 5 that we're having, you will find that here the ratio is small, but still a little bit far from 1. In the non-integral case already at 5, you have 3.79, which is not very far from 7.3. But of course, already at 5, we had some huge numbers, so we could not go beyond that. So the Diophantine approximation works. There is no doubt. It works perfectly, and you can have the answer for the dynamical degree. But in the case of in the integral cases, you need really hundreds of iterations to get some precision, to get really close to 1. And in the non-integral case, you can get some accuracy, but the calculations are heavier and heavier. In fact, in some cases, there are not the cases that have shown here. There's some other cases we have studied, where we studied that in detail. We had some integral case, and the ratio after 500 iterations was 1.004. And we have to double the number of iterations to get a little bit better precision on the last digit here. And the calculation was 30 times longer, which still is acceptable. But the non-integral case, we had a dynamical degree given by the ratio of the Diophantine approximation was 2.0 after 10 iterations, and 20 iterations gave a much better approximation. I had 3 digits converged, but the calculation was 1,000 times longer. So, okay, you can do the Diophantine approximation. It will work. It will give you some answer. It's a clear indication that the mapping is non-integral, but perhaps we would like to have something better than that. And the answer is, again, something that has been initially proposed by Rod Halbert. Yes, the same one who proposed the Diophantine approximation. Now, his approach was formulated for second-order mappings. We are going to see later on that we will not hesitate to apply to higher-order ones, but anyhow, let's start with that. So, Halbert has shown that in the case of second-order mappings, you can always take initial conditions where x0 is generic, meaning that it does not satisfy any constraint, any special equation. It is taken completely free. And then x1 is z that can take any value. And now what you do is to say that the degree is given by the number of preimages of this relation here, where you fix the value of w. Now you can understand that more or less. We have fractions iterated because we have fractions by iterated the mapping, and so this equation here you can write as a polynomial equation. You are counting the roots of your polynomial. So this is related to the degree, of course, directly. So that's why the degree is related to the preimages of the thing. And Halbert made the observation that if you do this for not any w, but one of the values that appear in singularity pattern, then the calculation will become greatly simplified. And the best way to see that is through an example. So we have again our mapping that have been working since the beginning of the talk. The confined singularity pattern is 0 infinity square 0, so that's okay. And then you ask the degree given by the preimages of, here I decide to work with the preimages of 0. It appears into place, and this is simpler. So, okay, so the degree obtained by the singularity 0 is given by the preimages of this 0. But when you have this in the singularity pattern, you have a 0 also 2 steps before. Or you could say, if I have that, then you have the preimages of these 2 steps later. But anyhow, this is the thing. And if you try to compute the degree associated to infinity, then infinity appears square only if there is a 0 before. So the preimages, the degree associated to the existence of infinity is related to the preimages of 0 that one step before. So we have the degree given by either by 0 or by infinity, expressed in terms of this z, which are the number of preimages of 0. But that's not the only source of infinity. This is the important thing here. Some other singularity exists, and this is a singularity where the pattern finite, infinity, appears periodically all the way. So now this singularity is not bad from the point of view of singularity confinement or whatever, because there is no way to enter the singularity. This singularity exists through the whole line. So this, and in fact, since the pattern repeats all the time, we call it a cyclic singularity, and the cyclic singularity is not an obstacle for integrability. But here, for our calculation, it is a source of infinities. So one step out of 2, you have some infinity. So this is exactly the source term here, which 1 out of 2 is 1 and the other one is 0. So this is a contribution to the infinities here, to the counting of infinities at that step. And when you put, and of course, calculating the degree based on 0 or based on infinity is the same thing. There is no difference. You calculate the degree, there's a degree. Any singularity will give you the same result. So this is what we call roughly a bit. This we call the balance in the singularities, mean the degree you calculate with one will be equal to the degree you calculate using the other. So balance in the singularities, you get this equation for z, and you solve it, and this is, of course, this is the solution of the homogeneous part, and then the degree, since we start with the degree at d0 is 0 and d1 is 1, you get this thing, which is exactly what we found empirically by just doing the iterations. So this method works perfectly in the integrable case, looking at the singularities and balancing them. And you can also do the same thing in the non-integrable case. Again, here we have this mapping where we know the singularities. The singularity pattern is 0, infinity to the fourth and 0. And again, you can say the premises of 0 is like before. You have a 0 and a 0 that was 2 steps before. And the infinity, okay, but with a multiplicity of 4 existed here, provided the 0 is, there is a 0 just before. So you can write this characteristic polynomial, and you are going to tell me, oh, there is a cyclic singularity here as well. Of course there is one. But if I only wish to compute the dynamical degree, I don't care about those source terms that I can add here. The dynamical degree is given already by the homogeneous equation. I get this characteristic polynomial, and this is a large root, the largest root. And if you remember what I found by the full deautonomization, that was exactly the same result. This is the thing here. But I said the term balancing the singularities before, meaning that I can balance. In fact, the example I'm showing is this one. I balance the singularities, associate the degree obtained by the singularity 0 and degree obtained by singularity infinity with the source term. And when I do this, I can write this table here, which gives me, by balancing the singularities at each step, I can find the degree with this term. And this is a very simple calculation that can be cast algorithmically. It uses only integer arithmetic. And when you, of course, it can be done also for the non-integrable case, provided we implement here the cyclic singularity as well. And while with every other method, for instance, the direct calculation when compute fractions and simplify, when you do the Diophantine calculations, it's very difficult to go even up to those numbers. When you do the balancing of singularities, there is no limit to what you can do. And you can obtain things like that in a fraction of a second, because this is only just integer additions, subtractions, and multiplication by small integers. So this is an instantaneous calculation, I would say. So now the difficult part starts, because up to now, everything, we were in a domain where more or less we're mastering everything. The second order mappings, there are exact results, there is a guide, we know what we're doing. How about going to higher order? That's the main thing. And this is, of course, this is an ongoing research. The point is there are no rigorous results. But what are the things that we believe? First, we think that full deautonomization works. We have several examples where you can show that full deautonomization for third, fourth, and higher order mappings works perfectly. Then the Diophantine approach. Diophantine approach, there is nothing specific about the order of the mapping Diophantine approach. You can work as well with higher order mappings, and we believe that always give the right answer. And then how about Halbert's method, balancing the singularities? This is the most delicate part, because remember, when I presented the method of Halbert for second order mappings, I said that you can always take x0 as generic, and x1, it is free to take any value. There we can put even constraint, ask that it takes a value that it gives something after so and so iterations. Now, when you have a higher order mapping, what is the prescription? In the second order mapping, this assumption that Halbert is making is without loss of generality. You can always do it. But when you are faced with higher order mapping, then there is no guarantee that what we suggest here is without loss of generality. In fact, what we do is we ask all of the initial conditions to be generic, except for the last one, in which you are going to calculate the degree in some sense. So this is an arbitrary assumption. There is no guarantee that this assumption is a correct one. But up to now, in every case we have examined, it works. So there may be pathological cases, but we have not found any yet. So before going to one or two examples, there will not be many, let me tell you what is known about higher order mappings. So first, there is some result by Silverman, which was that was shown on multiplicative mappings, monomial mappings, in fact. He has shown that the maximal growth in big N dimensions is like, yeah, I should have chosen another letter, said N to the N. It's a little bit ridiculous when you tell it. Okay, so the maximal growth is N to the power of the order of the mapping. That's what Silverman has shown. In fact, he has not shown that. He's shown only in monomial mappings. This is a conjecture that cannot be faster than that.
But Basile, sorry, there's an exponential factor missing. The prefactor, the growth can be exponential, but the prefactor can at most be that polynomial.
Yes.
Okay,
yes.
That's what you mean. So there's an exponential missing there.
And then Massesan has shown that when you have mappings that are reductions of Kp or BKP, then the growth can be only quadratic. And then Schiff has extended that for CKP, DKP. So there is a huge class of mappings that are reductions of a well-known integral equation, perhaps the most general one you can write, that have only quadratic growth. And then there is a result. We have an old result we had together with Ramassamy. When you have a Gambier mapping is a mapping that is a system of homographic mappings coupled in cascade, which means that one mapping is coupled to the one that is just previous to it. So have a homographic, then you add the homographic that is coupled to that, and a homographic coupled to that, and so on. And you have an nth order Gambier mapping, then the growth can be only up to that. So not the most general one. It's smaller than that. So when you look at the results, our conclusion is that if you wish to have a maximal growth, then you should couple a second order mapping with a sufficient number of linear mappings. This is the idea. Linear algebra can just be linear. This is that's the only way. And in fact, this is the way we have been constructing mappings with maximal growth, starting with some mapping that has quadratic growth and then coupling to that linear equations. Then you go to higher and higher degrees in n. So after that, I have to show you two examples that are a little bit special. The first one is an example that Massesan has found. And I like it because it's a very clever thing. Look at this mapping. I will not tell you what, to begin with, where does it come from. You will see it in the next slide, in fact. Take this mapping here. And then you compute the degree any way you wish, and you find that the growth is cubic. So already this mapping is order 4, but it cannot be a reduction of Kp or any because the growth is more than cubic. So is it a coupling of something? We'll see. But before doing that, let's do this method with the preimages and again balance the singularities. So the mapping has one confined singularity and an unconfined one. Now remember in the case when I present the results of Diller and Favre, I said that a mapping that is linearizable may have unconfined singularities. So finding an unconfined singularity here is perhaps an indication that some linearizability is there, hidden someplace. But already doing the calculation from the Hilbert's way balancing the singularities is quite straightforward. This is as always. And the infinity, of course, relate to that. And then there is a source term. And the source term, you have to look what is happening in the unconfined mapping, where every 3 steps, the exponent of the infinity is grown by 1. So this is the integer value of n over 3. And when you balance the singularities, you find the degree grows like that. And it reproduces exactly what you found there. So where does this mapping come from? Okay, first we can show that balancing the singularities give exactly the thing that we have found before. And then where does it come from? How did Ramassamy find this mapping? Well, this is simply the coupling of this is, to put it simply, is simply autonomizing a discrete Penlevé equation. Going to a mapping of higher order where you eliminate the explicit n dependence. So typically this discrete Penlevé equation has an an here that is exponential. An being exponential means it satisfies this equation here. And if you wish to make it autonomous, well, you eliminate an between this equation and this equation, and you go back to the mapping we had before. So this is the thing. You are coupling this equation here that has quadratic growth to a linearizable system, and this is why you are getting this higher than quadratic growth. You are getting a cubic growth. So it's the de-autonomization of a discrete Penlevé equation. It's autonomization of a discrete Penlevé equation, sorry. And then next example, this monstrous system that was proposed by Claude Vialet. Yeah, again, a 4th order system, but this one has a confined singularity pattern that is huge, and a cyclic pattern that is huge. And moreover, it's a little bit complicated because you can see this 4th order, so you need 3 initial conditions, generic and then a specific value. And you can see here I have 1, 2, 3 finite and 0, and here 1, 2, 3 finite and infinity. So in fact, in here in the cyclic pattern, there are hidden 2 cyclic patterns. You don't have only 1 cyclic pattern, but you have 2 because of this possibility here. So when you do the calculations, okay, I'm sparing you the details on the calculations, you end up with the characteristic polynomials. And when you do this, well, you find the dynamical degree, the largest root of those, the 2 equations that are right, the largest dynamical degree is that. And this works perfectly. And in fact, balancing the singularities, in fact, you get the same answer whether you do it by full autonomization or using the Hilbert's method. And balancing the singularities, you can compute the degrees explicitly. This is what I'm showing here. And it takes, in fact, you have to stop someplace because the arithmetic you are using, it starts requiring some special thing to go beyond 32 digits. So at some place you have to stop. Okay, so there are dozens of examples. You know, we like to look at examples. And this is the best way to do it before going to try to prove something. Have a sufficient number of examples that can convince you that what you are doing has a chance to be correct. So we have many examples where all the methods that were presented here work. Of course, there may be pathological, and we know there are some pathological cases where things do not work. Of course, I have avoided to present those cases here. It would have been rather difficult to enter into those complications. But of course, if you are interested, then plenty of cases that are not as nice as the ones I presented. And everything I presented here concerned birational mappings. So how about rational cases? Well, we have some results. The main approach we have shown here works also for rational cases, a little bit more complicated, but there is no fundamental difficulty. And of course, you can ask the annoying question, what happens when I have non-rational mappings? There, it's a real terra incognita. But I have the feeling that if you know the singularities of such system, whatever, any system, then you can say something about it. Once you have looked at it and you have some idea on the singularities, there is something to be done. This is a deep truth for that, or at least is my belief. And since I'm reaching the end of my seminar, I would like to end it again with an aphorism of our mentor, Kraskal Sensei, who, when we started working with discrete system, he said that we believe that the equations of physics were in differential form and they were the most fundamental ones. But in fact, now the more fundamental objects are the discrete system. And this is a good place to conclude my presentation. So thank you very much.
There are questions. Let's go ahead.
This has nothing to do, this is not, it's pure coincidence. It's not the Paris-Saclay mafia. So, yeah.
No, I confirm. So my question is about this quadratic growth, right? So it feels to me that something growing quadratically should have to do with some sort of statistical model in 2 dimensions defined on the domain of diameter n, but would grow like the area of this domain, which is n squared. Is there any?
In fact, I would agree. In fact, I would agree with you. And there are statistical models where we can show that the reductions go down to some discrete Penlevé equation, and so on. I don't think there is any rigorous proof on that. What Matheson has shown is for a very specific equation. This is the Kadovchin-Petersvili equation. He has shown that. But I have seen examples that are exactly in the direction you are mentioning. So I think this is correct, but no proof yet.
Question, if I'm allowed. In cluster algebras, this happens very often because evolved cluster variables sometimes tend to be interpretable as partition functions of dimers and things like this on growing domains that grow with how many mutations you make. So something like this growing degree, basically. And my question is also about singularity confinement. Is there some sort of general theory of singularity confinement in cluster algebra?
I don't know. In fact, the only domain where singularity confinement was known even before we discovered it, because we discovered independent of them, that was in numerical analysis. The only guys who knew about that and had established singular rules and doing exactly the business we're doing was the numerical analysis. I don't know whether anybody else has looked at the singularities. They have to do it, the numericists. Because they hit singularities, but I don't know if anybody else having done that.
Maybe as an answer to your question.
We continue with the French mafia. Let's be clear.
Paris Saclay Mafia still. So to answer your question, I think there was some work by Glick and also by Affolter, de Tillières, and Melotti on some recursions coming from cluster algebra and the singularity confinement.
I was asking more generally, right? Like,
it's the beginning.
Well, if I may, I mean, of course, there's a connection to the Laurent phenomenon as well. Yes, but only what in discrete integrability would be known in Hirota bilinear form. I would say you can actually state that the Laurent phenomenon is maybe not exactly equivalent to singularity confinement for those equations, but it's very, very close. Any other questions? Yes?
Basile, we know that for linearizable system, even the Painlevé test sometimes fails. In a similar way, why do you expect the confined singularity setup for discrete equations?
This is, well, the parallel between the continuous Painlevé and the singularity confinement, we believe that is something that is really true. And of course, you point out that in the linearizable case, the continuous, you don't have the Painlevé property, yes. And when you go to discrete systems, you don't have a confined singularity. But of course, a proof that one goes to the other does not exist.
Yes, I know.
And I don't think that it can be proven. But intuitively, yes, it's the same thing. Yeah.
Okay.
Any other questions, comments? Since there's 1.5 minutes or 2 minutes left.
So you have to ask a question.
No, I'm going to make a comment.
Let's hope it's not an embarrassing one.
It's not necessary to show page 5, but on page 5, you
page
have
5. Oh,
this quick overview of this.
That will be. Oh,
no, but it's not important.
Yeah, okay.
I mean, there was this quick overview of the famous theorem by Diller FR.
Yes.
And the quadratic case, I would argue, is also linearizable. Because integrable systems are integrable through linearization. We can't do better. Of course. So it's linearizable because it's basically it corresponds to addition on an elliptic curve.
I agree.
But it's not linearizable through a rational transformation, but you need elliptic functions to do it.
Yes, absolutely. Yeah.
What about the higher dimensional cases? Because already the example that you showed, the integrable case, the fourth order mapping that has cubic growth.
Yes.
You would like to call it integrable because it has very nice growth properties, but there's only one known integral. If you would like to have something like Liouville integrability, you would need at least 3, but there's no way to...
The point is, in this case, Ralphson, you just cheat, you know where it came from, do it backwards, and then you are scot-free. But if you are given a system,
exactly,
you look at the degree, and we have already discussed this thing. If it's cubic, already you know what's happening. But suppose it's higher degree, you don't know how those things enter, and then you are lost, of course. There is no surefire way to integrate a system. You say it's integral, yet you don't have enough integrals, and you know how to disentangle it. So yes, it's a mess.
I think the only case where there's some hope in higher dimensions to have some kind of general result would be a mapping on Pn that has quadratic growth. Yes. Maybe there you could hope for a general statement that there would be enough conserved quantities.
I believe that if it has quadratic growth, one way or the other, it will fall in the class of mass sum. If it's one way or the other, it will be there. But yeah, but it's till you find the counterexample. Ask the HIV people to find the counterexample.
I think it's time to conclude. So let's thank Basile again.
Thank you very much.